Okay, now today we will begin the chapter number 7. The first concept is of rigid body. Okay, now see what is rigid body. Whenever the distance between all pairs of particles of the system do not change, then this is known as a rigid body, or we can say interparticle distance in a body does not change, then we can say it is a rigid body. Okay, it's a special case, ideal case, which is never possible in day-to-day life, but we shall consider rigid body as an ideal concept for the different problems that we are going to discuss in this chapter. Rigid body is a body with perfect, definite and unchanging shape. Change of shape is not possible. Okay, a solid body can be deformed while a rigid body cannot be deformed. Okay, for many practical purposes, solid body can be treated as a rigid body. We shall take solid bodies, okay, as a rigid body. In general, they do not change their shape. That is why we shall take these solid bodies as a rigid body. There are examples: wheel, tops, steel beams, okay, molecules and planets. For a body, it can be ignored that they wrap, bend, or vibrate and treat them as a rigid body. Okay. Now there is a concept of translational motion. This concept is understood with the help of example. There is a rectangular block, you can see here. Okay, this is a rectangular block which is sliding down an inclined plane. Okay, without any sidewise movement, it goes this way only. Okay, now try to understand the different particles. Say particle p1, p2, any number of particles you can take. All these particles will start moving in one particular direction and they will move together, means they have the same velocity at any instant of time. Such motion of rigid body is in pure translational motion, we can say. All the particles are having same velocity. Okay, in pure translational motion at any instant of time, all particles of the body have the same velocity. Okay. Now let us consider the rotational motion. See here, one says sphere is there, or we can say there is a rigid body, solid, metallic or wooden cylinder you consider. Say for example, this is a cylinder. Okay. Now this is a cylinder which is moving in this direction. Now try to understand its motion. This motion is in this particular direction, okay, in this direction, as well as if it is rolling, then it rolls around this point, that is center. Okay, this cylinder shifts from the top of the top of the inclined plane, so it is coming from top to the bottom. Okay, and thus it has translational motion. So what is happening, it goes from top of the inclined plane to the bottom, so it is having a translational motion. It moves on a straight path. Okay, all the particles are not moving with the same velocity here. Try to understand. The particle near from the axis of the cylinder has less velocity, and particle for away from the axis of the cylinder has more velocity. So the particle here will have more velocity. The particle which is close to the center will have less velocity. Such type of cylinder which is having velocity which is not a pure translational velocity, is a combination of two motion, which is translational motion and rotational motion. The line along which the body is fixed is termed as axis of rotation. Now try to understand, if you consider this as a cylinder and this is a center, and we can say a line which is passing through this particular point, that is this point. Okay, that line passing is considered to be the axis of rotation. Okay, now in rotational motion what happens? all the particles which are in motion, that of rigid body, they all are moving on a circular path. Try to understand. Say for example, this is the cylinder and all the particles are going to perform the circular motion, okay, by keeping their centers on the axis. Okay, so all the particles which are that of rigid body, they are moving on circular path, and the center of all these circles falls on a definite straight line. Then the motion of this kind of body is called the rotational motion. Try to understand the motion of the top. The top is like this, okay, and it is moving in this particular direction. Then all these particles are moving on circular path by keeping their center on this axis of rotation. Okay, this kind of motion is called the rotational motion. Okay, we can consider the motion of our earth as a rotational motion. Okay, if all the particles of the rigid body perform circular motion and the centers of these circles are steady on the definite straight line, which is called the axis of rotation, then it is called the rotational motion. Okay, there are examples: ceiling fan we can consider, okay, potter's wheel we can consider, which is in motion, giant wheel in the fair, merry-go-round. All these are the examples of the rotational motion. See, now we shall discuss the characteristic of the rotational motion. In this figure, it is very much easy to understand. Say for example, this is a top which is considered here, okay, and this is the axis of rotation. Say for example, this particle you take, then it is going to move in this particular circular path by keeping the center here at C2. If you consider this P1 particle, then it is also moving on a circular path by keeping its center here on C1. So all these parts, if you consider one particle here, then it's moving on circular path by keeping its center here on this line. So all these particles of rigid body are performing circular motion. Okay, and they are keeping their centers on one fixed line, which is called the axis of rotation, and this kind of motion of whole body is considered to be the rotational motion. Okay, so it is explained here. The motion of the top is also shown here. Okay, it is also a circular motion of all the particles, but they are keeping their axis, they are keeping their centers on one particular line, which is called the axis. Okay, so it is also a rotational motion. Okay, if you consider the motion of the fan, okay, the moving fan, okay, here it will say it will move like this. Okay, so this the wings of the, we can say, fan are performing the rotational motion by keeping their centers here on this particular line. If this fan is moving in this way, okay, then also we can consider the motion of this whole circular face as a rotational motion. It goes this way, then it comes again this way. Okay, then it is also considered to be the rotational motion. Here its axis is like this. Okay, its axis will be like this, it will be moving like this. And if you consider the wings, or rather fan, okay, these wings if you consider, then they are performing the motion this way, then their center is lying at this particular axis. Okay, so there are two types of rotational motion. This way also it goes, and this way the fans are also performing, or rather wings are also performing the rotational motion. Now here there is a combination of the translational and the rotational motion. Try to understand the motion of this jug. Okay, now see this vertical axis, you try to understand this vertical axis, vertical line, or we can say it makes the same angle with this horizontal line throughout. Then this is a kind of translational motion. Okay, but if you see in this figure, then initially this vertical line is making say 90-degree angle. Now this vertical line has become slightly slanted, so it is making some less angle, then it goes this way. Okay, so what is happening, this jug is also moving in this say clockwise direction. Okay, as it moves on this particular path. Here this jug is performing only the motion on this particular path, while this vertical line and horizontal line, they both are having same angle throughout. Here these angles are decreasing. It may be possible that now this will slightly bend this way. So here there is a combination of two motion. One is this translational motion, okay, and one is this translational motion, and the other one is a kind of rotational motion of the body. Here only a translational motion is shown. Okay, so this is a combination of two motion. Here in this second case, here this is only showing you the translational motion, while here this is showing translational plus rotational motion. When a coin is tossed, try to understand, when the coin is tossed before the match, it goes this way as well as is perform the rotational motion. So it is a combination of the rotational motion as well as the translational motion. Okay. Now there is one important concept of system of particle. Whenever there are set of more than one particle, they are mutually interacting or rather intersecting each other, then that is known as system of particle, or we can say set of more than one particles. Okay, that is called the system of particle. Now there is a concept of center of mass. The center of mass of the body is the point where entire mass of the body is supposed to be concentrated. It is known as center of mass. Okay, you must have balanced the writing pad on your fingertip. You must have done this, okay, by keeping it here, okay, and you are rotating it. So this point about which you are rotating this writing pad, okay, then this point is considered to be, you cannot balance this at any other point other than this. Try to understand, you cannot rather balance this writing pad here at this point or this point. No, you will just be able to balance this pad at this particular point only. This point is considered to be the point where the entire mass of the body is supposed to be concentrated, and this is called the center of mass. Now there is an expression for the position vector of center of mass of the system of n particles in one dimension. Try to understand, there are n number of particles. Say for example, you have first of all two particles which are considered here, okay, whose masses are m1, m2, and they are situated at distance x1 and x2 from the center or other origin. We consider this as a Cartesian coordinate system. This is your x-axis, this is y-axis. This particle m1 is at distance x1 and m2 is at distance x2. Now center of mass is defined as m1 x1 plus m2 x2 upon m1 plus m2. So center of mass is located at the distance x from the origin as given by m1 x1 plus m2 x2 upon m1 plus m2. This is the point where the center of mass of the system is located. If there are n number of particles, then how will you write? It will become m1 x1 plus m2 x2 plus up to plus mn xn upon m1 plus m2 plus up to plus mn. This expression is given. If there are n particles, then m1 x1 plus m2 x2 plus up to plus mn xn upon m1 plus m2 plus up to plus mn, or we can say sigma mi xi upon sigma mi. You can write where sigma mi will give you the total mass of the system, which can also be written as m. So we can write this equation of our center of mass as x is equal to sigma mi xi upon the mass of the whole system. Okay, that is total mass of the whole system. Okay, it can also be written as capital M sometimes. Okay, so this can be replaced as capital M, that is total mass of the system. Okay, now if you have two particles only which are having the same mass, okay, then it is very easy to determine. Okay, here this is a special case which is discussed here. Okay, if you have two particles only but which are having same masses, then we can replace m1 and m2 by m. So what will happen? It becomes mx1 plus mx2 upon m plus m. So this becomes 2 times m. So it can be taken as common. So it becomes x1 plus x2 upon 2m. Okay, so x1 plus x2 by 2 will be the point where the whole mass of the two equivalent mass is having their concentration of the mass. Okay, or center of mass is located at the midpoint of these two same equal masses. Okay, now if you have the masses in two dimensions, okay, x and y axis are there. Okay, then what will happen? It will be having the x coordinate as well as the y coordinate. Okay, say first of all you have first mass m1, okay, whose coordinates are x1 y1. The other one is mass m2, coordinates are x2 y2. m3 is having their coordinates x3 y3. Then x coordinate of the center of mass can be m1 x1 plus m2 x2 plus m3 x3 upon m1 plus m2 plus m3. Similarly, y coordinate can be written, and center of mass can be written as, first we write the x coordinate, that is m1 x1 plus m2 x2 plus m3 x3 upon m1 plus m2 plus m3, and second we write the y coordinate. Okay, so it is very easy to understand. Okay, here if same masses are there, all the three masses are same, then how it will be written? Then m can be taken as common. Here in the denominator it becomes 3m. Okay, so it will be x1 plus x2 plus x3 divided by 3 and y1 plus y2 plus y3 divided by 3. Okay, and center of mass of the system formed by three particles of same mass will be at a middle of the triangle formed by these three particles. Okay, now the center of mass of three particles which are not lying in the line is written as, sometimes you can generalize this also, okay, as m1 into x1 y1 easily. You don't find them separately, you can write them in this manner also, m1 into x1 y1 plus m2 into x2 y2 plus m3 into x3 y3 upon m1 plus m2 plus m3. Okay, if n particles are there, then you just extend this for n particles, m1 into x1 y1 plus m2 into x2 y2 up to mn into xn yn upon m1 plus m2 plus up to plus mn, or generalize formula can be written as sigma mi xi yi upon m. Okay, this can be written easily, you can understand. It is m1 into x1 y1, so m1 2 3, that I is the common letter which is used here. And if you want to write for x coordinate, then m1 x1 plus m2 x2 plus up to plus mn xn. Y coordinate, it will be m1 y1 plus m2 y2 plus up to plus mn yn. Okay, it must be yn upon m1 plus m2 plus up to plus mn. So it is very easy to understand, as well as it is the easiest topic. Okay, now how to determine the, or rather how to theoretically estimate the center of mass of the solid body. Now you consider this is a solid body which is having small segments of this solid body, as they are having the masses dm1 dm2 up to dmn. okay, and their volumes are dv1, dv2 up to dvn, okay. And say for example the position coordinates of these first, second, third volume elements which we are considering small elements, okay, their position coordinates are r1, r2, then third one is somewhere here, then you consider the volume element which is having its position vector as r3, okay. This way you can consider. Now it is very easy, dm1 r1. Now see, here it is considered to be in 3 dimensions, so r1 will be, in general, if I write for the first, then it will be having x coordinate x1, y1 and z1. All the 3 coordinates will be there. It can be written as, it can also be written as, say r1 is equal to x I cap plus y j cap plus z k cap. This way these 3 coordinates can be written. x1 can be written for the first, second and third. It can be x1 I cap plus y2 j cap plus z3 z1 k cap. This can be written in this way properly. See, r1 can be written as x1 I cap plus y1 j cap plus z1 k cap, okay. Second can be written as x2 I cap plus y2 j cap plus z2 k cap. This way you can write the coordinates or in a vector form, okay. Now if you want to find the center of mass, then it's very easy. First mass is delta m1, or say small mass is delta m1. So delta m1 into position vector of first, that is r1, okay, it is shown here, okay. The position vector can be written as that of this rigid, rather solid body, is delta m1 r1 plus delta m2 r2 up to delta mn rn upon delta m1 plus delta m2 plus up to plus delta mn. And if you want to write in a short form, then sigma delta mi xi for x coordinate upon delta mi, and for y coordinate here it will be yi. Here this will be y coordinate, and instead of x you write z, then it becomes the z coordinate, okay. So it is very easy. Sometimes it is also written as number of particles are n is more, then delta mi is smaller, okay. Delta mi is very small value, and summation will turn into integration, so sigma dm will become total mass. Sigma dm, or rather sigma delta mi, can be written as integration of dm, and it will be total mass. So delta sigma delta mi xi, then it can be written as this sigma delta mi can be converted into the integration, so x, okay, then x into dm it will become. Then instead of this sigma delta mi yi, this can be written as integration y dm. Similarly this z can be written as, okay. So x coordinate of the center of mass will be 1 upon m into x dm. Similarly y coordinate will be 1 upon m into y dm, okay. Z coordinate can also be written as 1 upon m into z dm, okay. This is very easy to understand, okay. See here you can understand this properly. In this sigma delta mi xi is now converted. Here sigma delta mi is taken as dm, okay. So it becomes integration x dm, and this sigma delta mi will become total mass. So the x coordinate can be 1 upon m integration x dm. That is shown here in this lower part, okay. Here see, this is written in this way, okay. Then z coordinate is converted and y coordinate is also converted, okay. if we choose the center of mass as origin, then this x, y and z coordinates will be 0, 0, 0. Okay, so we can have r dm integration will be equal to 0. Okay, so we can say x dm is equal to y dm, that is equal to z dm, that will be 0 if we choose the center of mass which is lying on the 0, 0, then it becomes. Okay, now we want to find out the center of mass of the thin rod of uniform density. This is the uniform rod which is having uniform density, and if the total mass of this rod is say m and its length is taken as L, then its mass per unit length, means mass of 1 centimeter length or 1 meter length, will be m upon L, which can be denoted by lambda here. So first thing we are considering that what is mass per unit length is m upon L. We consider that its midpoint is an origin. This is your x-axis. Okay, both the side we consider a small mass dm which is at distance x from the origin. Okay, now x coordinate is 1 upon m, x dm is our formula. Okay, so only x coordinate will be there. This is only a one dimensional case. Okay, so dm is equal to lambda into dx. Say for example, this length of very small element is dx. Now see, mass per unit length means 1 centimeter is having the mass m upon L. Then what is the mass of this dx? Then it will be multiplied by it. So m upon L into dx will be the mass of this very small element whose mass is denoted by dm. Okay, so here the mass of this small element is m upon L into dx, where L is the length of this rod, capital L is taken here. So now x coordinate according to our equation 1 upon m x into dm. Okay, so instead of this dm small mass, we write m upon L into dx. So it is written instead of this dm, m upon L into dx into x. Now m upon L is constant. Okay, and as such m will be cancelled out. You can see here m and m will be cancelled out. You will have 1 upon L. Okay, integration begins from 0 to L x dx, because the whole length is L. Okay, so now just we have to integrate. Integration of x will be x square by 2, upper limit and lower limit are written. Okay, then instead of x you write first L, so it becomes L square by 2, and one L will be cancelled out, so it will always only remain L by 2. So at the midpoint, that is at L by 2 distance, the whole mass is concentrated, and this can be easily understood if you want to balance this rod. So you have a one stick, and if you want to balance, then you have to keep your fingers at the midpoint of this uniform rod. Okay, then or we can say at L by 2 distance, okay, from one end the center of mass is located. Okay, there are different shapes which are having their geometric shape and center of mass which are discussed here. If you have a sphere, then its center of mass is at center. If you have a disc, then it is also at center. In solid cylinder, if you have middle point on the axis, if you have this kind of say square or rectangle, then it is the intersecting of the hypotenuse or other diagonals. Okay, if you have this kind of triangular planar laminae, then it will be the point of intersection of the medians. Okay, point of intersection of median will give you the center of mass. If you have uniform cylinder, then it will be a midpoint or center of the rod, we can say. Cubic block, then it is again the point of intersection of the diagonals. Okay, then if you have cone, then on the axis of the cone near the base means at the lower part the center of mass will be there. If you have circular ring, then it is the center of the ring, and hollow cylinder, then again it's the middle point on the axis of the cylinder. Okay, try to understand this 2-3 times, read it. Okay, thank you very much.